Hi everyone, and thank you for being here. Today I'm excited to present our work titled QuadraNet V2 Efficient and Sustainable Training of High-Order Neural Networks with Quadratic Adaptation. This research was a collaborative effort between George Mason University, Microsoft, the University at Buffalo, and Peking University. My name is Chen Huixu, and I will be guiding you through how we are making next-generation AI models both more powerful and dramatically more sustainable to train. As we look at the current landscape of deep learning, we see that high-order neural networks are emerging as new state-of-the-art architectures. We are seeing this evolution unfold through advanced models like HARNet and vision transformers. However, these advancements comes with a massive, often hidden cost, the pre-training cost crisis. Training vision models on large-scale datasets requires an unsustainable amount of computation. For instance, pre-training a vision transformer H model on the ImageNet 21K datasets demands approximately 56,100 GPU hours. Financially, that can be amounts to hundreds of thousands of dollars. Even worse, every time a new architecture is introduced, we are forced to train it entirely from scratch. This means we are effectively discarding millions of dollars of prior investments in perfectly good legacy pre-trained weights. While adapter-based approaches exist, they often fail to capture the architectural performance improvements that these new models offer. So why can't we just reuse those old weights? The challenge lies in the adaptation. Modern high-order neural networks like HARNet and MorganNet possess complex architectural structure that fundamentally prevent the direct reuse of weights from standard pre-trained linear models. When we look at popular adaptation techniques like LoRa, we find a critical limitation. LoRa-based adaptation is designed to capture only linear distribution shifts. In the real world, the shift between pre-training data and the downstream data is highly nonlinear. Because of LoRa relies on a linear transformation matrix, it struggles to model this complex shift and cannot deliver the necessary performance improvements on original tasks. To solve this, we introduce the Quadratic adapter. First, the linear base. This part is directly inherent and frees the weights from an already pre-trained linear models, such as QuadraNet and ResNet. Second, the Quadratic adapter term. This part is initialized to 0 and is then trained on the downstream task to specially learn the nonlinear distribution shifts. Instead of a standard linear transformation, we upgrade the neural to a quadratic form. The mathematics looks like this. This formula is a core insight to our work. It decomposes a complex quadratic neural into two distinct parts. This approach is architectural agnostic because the quadratic term is embedded directly at the neural level. It works seamlessly with standard linear DNNs without requiring a complex redesign. Ultimately, this allows us to take a standard pre-trained model and instantly upgrade it into a high-order neural network, saving the massive cost of pre-training from scratch. Our proposed QuadraNet V2 framework operates in a streamlined three-stage pipeline. The stage 1 is initialization. We simply pull existing community pre-trained weights like those from Hugging Face to initialize conventional models like QuadraNet or ResNet or Vision Transformer. Stage 2 is adaptation. We introduce the quadratic adapter to the downstream task. We train only this adapter to capture the data's nonlinearity. and the stage 3 is inference. The turn model now operates entirely as a high-order quadratic neural network. Furthermore, we utilize external acceleration via Quadratic to ensure highly optimized inference speeds. To ensure this adapter does not become a computational bottleneck, we implement two crucial efficiency optimizations. The first is low-rank decomposition. This reduces the complexity of the quadratic term from n squared down to O2kn. It also enables early release of intermediate products, effectively halving memory consumption during training. The second optimization is Arturo's quadratic connection. This specifies the adapter by selecting trainable weights in a dilated pattern, which allow us to leverage existing highly optimized dilation convolution operators for incredible speeds. The results of these optimizations are remarkable. We achieved a massive reduction in GPU training hours. For large-scale models, QuadraNet v2 reduces GPU's training hours by 98.6% compared to training a HARNet L model from scratch. When compared directly against LoRa on a large-scale model, QuadraNet v2 required effectively the same compute time but delivered a massive 2.7% gain in top-line accuracy on ImageNet 1K. So looking at our ImageNet and Microsoft's Cocoa benchmarks, QuadraNet v2 consistently outperforms competing linear models like QuadraNet and high-order models like HARNet and MogaNet. The key takeaway here is that QuadraNet v2 achieves this state-of-the-art results without the expensive large-scale pre-training from scratch that other high-order models require. Beyond performance, our method is universally compatible and budget-friendly. For example, when applying traditional linear adapters like LoRa to a swing transformer, performance actually degrades. However, our quadratic adapter successfully improves performance by 1%, proving its architectural agnostic capabilities. Furthermore, QuadraNet v2 excels under extreme budget constraints when training time is strictly limited to a maximum of 275% CPU hours. Traditional high-order models fail to converge, while QuadraNet v2, however, reaches optimal performance even in these extremely constrained environments. So, in conclusion, QuadraNet v2 makes high-order neural networks accessible, affordable, and sustainable. We eliminate the needs for expensive pre-training by intelligently leveraging the legacy pre-trained linear weights. By shifting adaptation to the neural level, we successfully capture non-linear distribution shifts in an architectural agnostic way. With our low-rank and Arturo's optimizations, we achieved extreme efficiency, reducing GPU training hours by up to 98.4% compared to training from scratch. Finally, our future work will focus on extending QuadraNet v2 into other modalities, including large language models and diffusion models. That's our presentation on the QuadraNet v2. Thank you for your listening.